My name is Apollo Ibanez. I'm from Cal State San Bernardino. I'm a master's student and I do work mainly on tendon research, such as tendon remodeling. We looked at titin isoforms in frog muscle and how that affects viscoelastic properties. So titin is a protein found in the sarcomeres of muscle, and it affects passive muscle forces and muscle stiffness. And that can vary depending on how long or short the titin is. I've never worked with frogs before, so it was like a new vertebrate to me, and I wanted to get kind of like a broad range of research-related work among all animals, so not just one species, but like across all species. So titin is important to know and how it affects muscle properties because certain muscles might be more compliant than others, and that stiffness property may affect other things such as locomotion control, power performance, shock absorption, things such as that parameters.
My name is Hannah Chow, and I am a second-year student here at UC Irvine. For our project, we decided to research a compound called genopin, which comes from plants, and we wanted to see how this would affect tendon properties in rat tails. So by studying tendon properties in rat tails, we want to see if these results can be shown in humans so that we could use genopin for tendon rehabilitation. So for our findings, we didn't really see too many significant differences between failure strain between our groups, but with a larger sample size, we'll want to see if these differences will be more prominent in the future. In the future, we'll want to see, instead of using dissected rat tails, we'll do a lot more in vivo studies to see how genopin may affect rats in motion. I think the most fun part about working with MC is just being able to collaborate with a wide diversity of people. Whether I was working with people that had a really big understanding of what I was researching and people who had no idea what I was researching, it allowed me to improve on my communication skills and to show my findings with others.
I'm Cody. I'm a student here at UCI. I'm a rising fourth year, biosci major. My project was P20, focusing on human balance and developing capacity tests to see how that might affect how people balance. This test was focusing on tandem balance in different people. Tandem balance would be when you're walking on, for example, a tightrope where you have one foot placed in front of the other and you're trying to maintain balance, yeah. We came to a few conclusions from the study. We found that, for example, ankle proprioception is extremely important. So being aware of how, when you place your foot, where it's going to be your ability to maintain stable ankle.
My name is Leah Houston. I am from Cal State Fullerton, and I'm a kinesiology student minoring in aging research. I worked with the amazing Dr. James Finley in the USC Locomotor Control Lab, where we worked on perturbations and how it affected our proactive and reactive balance control strategies. What we did in the lab was trip ourselves and trip others. So that also included putting markers on different parts of the body and motion capture with different programs like Visual 3D, QTM, all sorts of different programs. What I learned from tripping people is that there is a funnel effect where we can look at the leg, what is happening at the leg, kinematic, kinetic forces. Then we can look at the joint and dive into muscle activation and timing and everything like that. Potential future direction for this work is utilizing EMG to locate and identify what muscles are working in proactive versus reactive balance control strategies. The best part about doing the IMSI research was finding who I am. I have never felt more myself, being independent, learning confidence. I just grew so much as a person in both the lab and in life.
My name is Ruby Tapia. I'm a recent UCI graduate from the Department of Biomedical Engineering. I'm actually going to be a first-year PhD student at Northwestern. So the project that we worked on was an in situ prep for the guinea fowl algae gastroc. So essentially what we were looking to do is use a previous work that was found in vivo studies and bridge the gap between in vivo and in situ work together to essentially help build better muscle models using in situ prep. Over the summer, the data that we collected was force outputs from the lateral gastroc of the guinea fowl. And then using these force data, we then create our force length curves. So the benefit of learning a lot of comparative physiology is essentially, I can't do in situ preps in a human, right? So that would mean I would have to put a human under anesthesia, cut your Achilles tendon, apply a bunch of stimulation to the muscle and then observe, what are the force outputs, right? The goal here really is to connect in situ data with in vivo data to help us make inferences about how complex dynamic movement is in real life.
My name is Apollo Ibanez. I'm from Cal State San Bernardino. I'm a master's student and I do work mainly on tendon research, such as tendon remodeling. We looked at titin isoforms in frog muscle and how that affects viscoelastic properties. So titin is a protein found in the sarcomeres of muscle, and it affects passive muscle forces and muscle stiffness. And that can vary depending on how long or short the titin is. I've never worked with frogs before, so it was like a new vertebrate to me, and I wanted to get kind of like a broad range of research-related work among all animals, so not just one species, but like across all species. So titin is important to know and how it affects muscle properties because certain muscles might be more compliant than others, and that stiffness property may affect other things such as locomotion control, power performance, shock absorption, things such as that parameters.
So you can control them. You guys able to hear me? Can you guys hear me online? Yeah, okay. Pop-up team, would you be able to share your slides, and you can go ahead and start your presentation when you're ready.
They need to make sure they unmute.
Yeah, and make sure you unmute yourselves to speak. Hopefully we don't run into too many technical difficulties this morning. Are they?
Yes, we're here.
Okay, great. Thank you.
Do you want to bring up the slides?
Sure, yes. Sorry, I can't hear you very well, Victoria. I think you may be muted.
Okay.
I think maybe just speaking up, we need to put the mic closer to the
Where is
That's
the
not
mic?
like the-
Yeah. This mic is for the live stream. Right.
Can you hear us in the room in general if I speak?
Yes.
Okay. So it's
Okay.
probably just a projection thing. So I think we should use this.
Okay. Yeah, sorry, I wasn't projecting because I thought I was just speaking. Okay. All right. All right, cool. Can you guys hear me better now?
Yes. Okay, I'm gonna be sharing my screen. So. Can everyone see?
Yes, we can see.
Okay. All right. Alrighty.
Yeah, could you make that full screen?
Oh. Is this okay?
Yeah, that should be good.
Yeah.
All right, go ahead, start when you're ready.
Hello, my name is Georgia, and I am joined by the other trainees, Promise and Athena, to discuss what we've been working on in the Pop-Up Movement Science Arenas project.
Okay, so for our agenda today, we're going to briefly introduce our principal investigators first, followed by us trainees, and then we'll be stating our purpose, so going over our research question and objective, and then we will show our data that we've gathered throughout the project so far, and as well as how we've analyzed that data. Then we'll go into future goals we have for the project, and if we have any questions at the end.
These are the principal investigators from our project: Jill McNick-Gray, Kelly Sharp, and Nidhi Sithapathy.
Hi everyone, I'm Athena. My focus for this project was setting up a pipeline to analyze our videos using pose estimation software.
Hi everyone, my name is Promise. I was in charge of collecting some of the 2D data via my drone, as well as coordinating some of the drone safety regulations on our UCI campus so that we're able to be capturing data in the fall.
And hello, my name is Georgia. My role in this project was to collect 2D data using a stationary iPhone camera, and I will also be working on the IRB for our upcoming pop-up labs.
Our overall research question we wanted to tackle was, how do humans and animals navigate challenging environments? How do they make contact with varied terrain while adapting to spatial constraints?
And our objective was to capture movement footage and use pose estimation software to determine foot placement strategies relative to center of mass trajectories. Our goal is to determine what individuals value in their decision-making approach on various terrain.
Okay, so now we'll go into our data gathering section. So here we see two aerial videos captured by my DJI Mini 3 Pro drone, and they show participants walking in a staggered formation from a sagittal perspective, which really gives us a better viewpoint when we are calculating this data and trying to visualize where joint segments are in the body. So as you can see, the drone in the first video is at a low altitude at about 7 feet above ground level, with the camera angle about 25 degrees below the horizontal. And it's about a 20 feet distance away from the participants to give a safe measuring point. And the time of day was about late morning, so it was easier to capture data because the light is optimal for this time of day. And then in the second video, you see there's some shadows by the overhanging trees, but that doesn't take away from the clarity of the participants. There's also a lot of changes with the type of clothing that the participants are wearing, which we'll get into later and how that's important when it's being run through the software that we'll be using. Some potential benefits of having a moving camera, such as a drone, is that it has this fixed lateral perspective you see. So the camera is fixed in the lateral, but it's moving along with the participants, keeping them centered in the frame, so it follows the trajectory of the subjects.
And my footage shows a view in the frontal plane of the participant walking and was recorded using a stationary iPhone camera. Prior to collecting this footage, the participant was prompted to wear tight-fitting clothing to support the visibility and subsequent mapping of body points for pose estimation software. Some potential benefits that a stationary camera offers are the clear reference point it provides for center of mass trajectories, the closer view of the participant, and convenience of use, since many individuals have access to a phone camera, and this type of camera is applicable in a wide range of settings and environments.
Our next step in the data collection process is using software to extract the coordinate location of several joints across our collected videos. Getting the numerical representation of the body would allow us to apply calculations to find physical properties like moment, angles between joints, and angular momentum. We first experimented with AlphaPose, which is a software that can automatically detect the human form and can distinguish different people in crowds. We tried it on a couple sample videos and made sure to include some videos where subjects are moving in ways that the model is likely not trained on, like the breakdancer. And as you can see, AlphaPose is much more accurate on a standard gait pattern, like the runners, and makes more mistakes with the unique movements of the breakdancer. This matters a lot to us because a large data set in our research project is diving footage from the 2012 Olympics. Within our broad research question, we want to know what kinematic features of a dive can best predict overall execution. How far can a dive be simplified to only a few key measurements of the body? Unfortunately, diving is a pretty unique movement, so when we inputted a diving video into AlphaPose to test, on the next slide, you'll see that it didn't work very well at all. AlphaPose is much better at detecting and mapping the people in the audience than it is the diver flipping in the air. The output from AlphaPose on diving videos was pretty unusable, so we wanted to find a software that could adapt to unfamiliar movements. Next, we found DeepLabCut. DeepLabCut is a software that was specifically designed to track the movements of animals, and the process contains many more steps than AlphaPose. First, the user defines the parameters of the project, like names of all the key points, the P cutoff, number of frames to pick, size of dots, etc. Then the user extracts frames, either automatically or manually, and the user labels those frames with the inputted key points from earlier. It's here that the user defines the form and movement of the animal, which was great for us because we had to be able to tell the machine how to expect the diver to move. Those are all the laborious steps, and what's left is to train the network, then generate the output and visuals in the form of plots and videos. And as we expected, on the next slide, the results are much better. The labels in the video output are much more accurate, and the plots clearly track the trajectories. Plot A shows the coordinates of every key point across all frames on one XY graph, and plot B illustrates how each key point moves as the video progresses. We also included a label on the N in the background because the fulcrum of the board is not visible, so we needed a stationary point to be able to measure board deflection. One note about DeepLabCut is that it's very sensitive to obscured body parts. The GitHub recommends that if in a specific frame a body part is not visible, to just skip it and only label the body part in frames where it is clearly visible. For this reason, it's a good idea to label body parts that are very easy to distinguish. In the case of divers, typically only one side of the diver is visible. So we focused on making sure that only one side was labeled well and assumed that the diver's body was roughly symmetric. Another place this came into play was labeling the back of the diver. We had to decide between labeling down the midline of the trunk, which would allow us to find center of mass, or labeling along the edge of the back, allowing us to measure curvature. For DeepLabCut, we were much more likely to get a better output if we labeled the edge of the back, because it's rarely obstructed by the arms and it's very identifiable by DeepLabCut's algorithm. When the diver is in a crouched position, it was difficult for us to see where the midline would be, so DeepLabCut would have an even harder time finding it. That's why we went for labeling the edge of the back instead. And the obvious consequence of having an accurate result is a necessity for a detailed input. For a video to come out like this, we needed to label 70 frames, and the whole video has around 800. For 150 diving videos, this is a lot of frames to label, so to find the balance of how accurate is accurate enough, we created a spreadsheet template that measures the variability of important segment lengths. The labels tend to wiggle around their exact location on the body throughout each video. We wanted a way to measure which key points have more unstable predictions, and if there were certain input videos that were labeled better than others. We are using the output data produced by DeepLabCut after it has finished processing a video. The data is formatted in columns of X coordinate, Y coordinate, and likelihood, and in the image on the slide is a small excerpt of the output data showing the coordinates for the right angle. We set our P cutoff to be 0.3, so only points with a likelihood of 0.3 or higher are plotted. And so the first step of data analysis was weeding out the low likelihood points, which are highlighted red. Next, we calculated several segment lengths, and highlighted in pink are any lengths where at least one point is low confidence. Any outlier segment lengths are highlighted yellow. Segment length was a good measurement to use to measure this wiggle, because there are a few lengths that should never change, like the distance between the hip and knee, and the total length of the back, for example. And next, on the third page are the statistics. So mean, median, variance, standard deviation, and relative standard deviation. We also have the trimmed stats, where we exclude the outliers. We weeded out all the output data with a likelihood of 0.3 or lower because we didn't want any low confidence data to impact our statistics. In the future, we want a way of defining what is good and bad from these numbers. we want to establish a meaning for a relative trend standard deviation of 0.2, for example, and be able to determine if that is accurate enough for when we use these data outputs in our future calculations. Next, we have some pros and cons between the two algorithms, because we have to decide from now on which one we want to use. DeepLabCut can run on pretty much any device and even has special CPU-only versions, as opposed to AlphaPose, which is only compatible with an NVIDIA GPU. DeepLabCut is also very user-friendly, and the process can almost entirely be completed through GUIs. The structure is also quite different from AlphaPose. AlphaPose uses its pre-trained model of the human body to find key points and label them throughout the input video, and videos can only be processed one at a time. With DeepLabCut, the user can start a project with as many videos as they want, and after supplying labels for some frames for each video, DeepLabCut is able to fill in the gaps. Labeling videos in DeepLabCut can take a while, sometimes over an hour, but this time is made up during processing. Using a GPU for both, the processing speeds for a video in AlphaPose and a project with only one video in DeepLabCut are roughly the same. However, having multiple videos in one training dataset in DeepLabCut doesn't lower the processing speed very much, so running a large collection of videos can be finished quicker with DeepLabCut. For diving, DeepLabCut is the much better option, but our future datasets will include more simple tasks like walking or running, actions that AlphaPose would likely be good enough for. DeepLabCut tends to struggle with casual videos like these because it is so sensitive to clothing, coloring of the subject or the background, and obscured joints. The reason we're not fully confident with using AlphaPose for walking and running tasks, however, is the availability. We do not have consistent access to a GPU that can run AlphaPose, so it would take us a long time to finish video processing. So our decision on which algorithm to use for simpler tasks depends on which takes longer, finding enough processing power for AlphaPose, or labeling enough frames for DeepLabCut to produce a satisfactory result. For now, we think DeepLabCut is the better option. We will just have to think very carefully about how we collect our data, as we'll see on the next slide.
Okay, so as Athena mentioned, we really want to highlight the importance of attire in this kind of post-estimation. So specifically with DeepLabCut, it is very sensitive to clothing, baggy, tight-fitting, as well as color of clothing. So as you can see in the video, one of the participants in the front, which is my mom actually, you can see how the segments kind of fade in and out as the frames go on in the video. And this kind of shows how it's really important for the knee joint, especially to be exposed when identifying it through the software. So after this video, when we ran the next trial, I had her wear leggings and it worked much better. Also, we want to highlight this can be relevant in other studies with other types of animals, other species. So in animal research, visible markers are often placed directly over the fur to aid in motion tracking, so to make those joints more visible that way.
And for anyone interested, we have created a tutorial on using DeepLabCut on a Mac device. The link to the document is on this slide, or you can also find it in our project Google Drive pop-up movement science arenas. It's in the folder called Analysis Code.
Okay, now we'll go over some future goals we have for our projects.
In fall 2025, we plan to recruit dance students from the UC Irvine Clark River School of the Arts to test their center of mass and decision making as they walk across a narrow balance beam. As the title of our project indicates, we'll be conducting this test in a pop-up manner where the materials are portable, making them easy to travel with across the UC Irvine campus. We will be capturing this test with the perspective of both a stationary iPhone camera and a drone camera, which will allow us to capture frontal, sagittal, and vertical viewpoints.
We also have several goals on the technical side. Our most immediate goal is we want to see if we can use the coordinate locations of key joints to calculate kinematic properties of dives, like the moment of inertia of different segment lengths, angular momentum, linear momentum, and so forth. Also using our output coordinates, can we train a machine learning model to be able to watch a dive and be able to score it on its own? We found the scores that each dive in our dataset received, so we would be able to give that information to an ML model. And this focus on dives connects back to our overall research question of what do individuals value most when making decisions on movement. in the context of diving, we care about how far we can simplify a dive. Does something like angular momentum generated during takeoff correlate to overall execution? We want to see if there's one specific feature of a dive, kinematic or not, that has a high correlation with score. And if there isn't one feature that can predict score, what's the lowest number of features that we can simplify a dive to? And to extend this broadly, using the results from our diving data set, we want to determine if there are any specific features that define movement in general. And to answer this question, we may want to apply this diving model to other sports. Does a simplified model of a dive also apply to figure skating jumps or hurdle jumps?
And then another big goal we have is slowly transitioning from this 2D data collection to more 3D. So we would be integrating wearable motion sensors such as IMUs, inertial measurement units, or optical markers. So this would greatly increase accuracy in joint position tracking rather than solely basing it on the software-based pose estimation like AlphaPose and Deep Lab Cut. And then we also want to incorporate multi-perspective drone footage to enhance spatial analysis. So in addition to the sagittal profile perspective, we want the vertical axis view as well as the frontal. So we can start to mesh these viewpoints together and create 3D models through a process called photogrammetry. And then one key consideration in this process is what we mentioned earlier, the importance of form-fitting attire in these kinds of sensor data capturing things. So we really want to minimize obstruction and improve precision in the sensor readings overall. So, yes. Do we have any questions?
Great, thanks. That was a really, really great presentation. One important thing in dives is like how vertical you are. Do you have a sense of what vertical is from your camera view?
For our diving footage, we only have the like profile view, and so we could measure vertical distance based on stationary points in the frame. We have a couple labels in the background that are stationary. We also are measuring the tip of the board, which does move, but in relation to kind of the pseudo fulcrum of the board, we might be able to measure vertical distance achieved. Yeah.
Great, thanks.
All right. One more quick question.
I have a question. When you guys are eventually look at all of these things in diving, how are you going to be determining the success of the dive? Are you going to be going based off the scorers, or are you going to be using other metrics?
We're thinking of using score. I think it's the most available metric for success that we have. It's also something that is relatively standardized. So yeah, for us, also in the future, for our future data sets, we are focusing on tackling scoreable tasks. Like for walking across a beam, we want to know if they fall off or not, stuff that's easy to measure if they succeed or not. So yeah, for dives, we're gonna focus on score and use that as a metric.
I think James has a question.
Yes, James online, if you have a question. Last one.
Yeah, so yeah, also really great presentations, really interesting stuff. I think many of us are interested in, when and where we can use these markerless motion capture methods. So my question was specific to the drone footage. I believe in what you presented, you were showing the results of Deep Lab Cut, and I was wondering if you've tried AlphaPose on the drone footage, specifically to understand whether the fact that AlphaPose uses a sort of human-based model or prior, if that actually gives you better results than trying to use Deep Lab Cut.
Yeah, we haven't used AlphaPose on the specific diving footage that Promise provided yet. We're kind of basing our assumption that it is better on gait pattern based on the sample videos that we gave at the beginning of this project. But yeah, it is worth trying it out before we can actually decide if it is better. You're just assuming that for now.
I have a question for Promise. Promise, have you, so currently is it one drone or is it it's one drone right now,
It's
right?
one.
Yeah. So have you thought about sort of how you might deal with calibration? And also I'd like to understand a little more deeply how it's actually tracking the people in the frame. I've never used a drone. So how does it do that?
Oh yes, so I did it all manually for these videos. I could have used this really cool auto tracking feature on the drone, which kind of you select the subject and it follows them, which I will be using for future trials just because, to keep it more accurate so that it doesn't shift at all. But what I said about the fixed lateral perspective, like I wasn't moving the lateral control at all, or I was moving the lateral control, but I wasn't like shifting the drone up or down in altitude. So it was maintaining altitude, but just hovering. And yeah, so I tried to capture it at a good distance away and everything so that it could be processed well. Lighting is a big factor as well, so I tried to do everything outdoors and kind of select like a good time of day for that. So yeah, that's like kind of my thought process going into it. Like I need to get good optimal weather conditions. I need to keep this drone as stable as possible. And then like I said, there's a way of combining all of these perspectives, so the sagittal, frontal, and vertical, through photogrammetry, which is something I've done in mapping with the drone. It's not really related to like capturing human like photo or video, but I've done it with like topical like land and everything, like creating 3D models with that. So yeah, it's really stretching my like I guess experience and getting like more human like data. Yeah.
Okay, we're
And
gonna have to
data.
stop.
We're gonna have to stop there. Thank you guys so much. That was a great
Conversation in Slack chat.
Yes, absolutely. Please do continue the conversation in Slack chats. This is a great topic for you guys have done a great job, so thank you again. Okay, and next we have Brian Olmo, and he's going to talk to us about science communication. Okay, so let's see. Let's pull yours up.
Oh, spoiling the end.
Let's see. Where is it? Oh,
Still spoiling the end.
I know. Sorry about that.
It's okay.
Let's...
Glad I didn't put anything too important there.
Okay, sharing screen. All right.
Okay. I'll hold this. All right. Hello, everyone. My name is Brian Olmo. I am the Communications Fellow for IMSI, and my project was Science Communication in Movement Sciences. My PI was the wonderful Dr. Christian Hubicki, who is currently working the live stream. Hello, everyone. So, before I get into the nitty-gritty of my project, a little bit about myself. I'm a recent college graduate from FIU, that's Florida International University. I come a long way. And before working for IMSI, I had roles as a video production intern for NASA, news desk intern for NBC Sports, photo office intern for the White House, and I was a communications fellow for NASA just before joining IMSI. The common thread, as you see there, is a love of media. I love telling stories. I've always loved telling stories. And I've always had a keen interest in science and math. I was just never very good at it. So that's why I started, writing about it. A couple photos of me just to illustrate my point. That is me at the Neutral Buoyancy Lab in the Johnson Space Center in Houston, Texas. And that is me on the South Lawn in front of the White House. Just so you know, I'm not lying to you. Project aims and background. So we wanted to communicate the findings of IMSI projects in a fun, easy to understand way for general audiences. We wanted to give visibility to IMSI's members via recorded interviews and short, highly edited videos. And we wanted to finally establish a social media presence and various channels for IMSI. By the way, if you like the LinkedIn post, I love you. Thank you. Very, very kind of you. So before I dive any further, there's a couple of terms I need to define for you in order to fully understand my process. These terms include things like B-roll. Just out of curiosity, if you can just raise your hands here, how many of you know what B-roll is already? Does that term sound familiar? Okay, so actually a pretty good amount of you. But just in case, B-roll is supplementary footage that goes over the main footage of someone talking, and it provides context. Think of newscasts, right? If you've ever seen a newscast, it's not just a guy talking for 20 minutes straight, because that'd be really boring. Really boring. And another phrase you're familiar with is a timeline. Very simple. It's used in just about all video editors. It's where you place your footage. And if you don't know what that looks like, that's what it looks like. The top layer is your video. I labeled it A, and the bottom is all the audio channels you'll have. That is B. So far, so good, I think. So what about the tools I use? So there are a bunch of different video editing softwares and design tools you can use. For my purposes, the ones that I found best were using Adobe Premiere Pro for video editing and Photoshop for design. And I like softwares in comparison to other options purely because I feel like my audio is like
Summon in and out. Clip it to your shirt, your
yeah,
collar,
let's do
and then it one position.
Yeah, let's do that.
And then it will be more consistent.
If it's too close, you get the P's do a plosive sound. So okay, that is much better. All right. So for video editing, I like using Adobe Premiere Pro. There's a lot more customizability there compared to other sort of editing softwares. And as for design, I do almost everything in Photoshop. It's just my tool of choice when it comes to editing. There's things like Canva, but I think Photoshop provides you with more tools and it's just a more powerful resource overall. So let's talk about the value of a cut. Vocal fillers are an inescapable part of the way we speak. These include ums, uhs, basically, like, etc. And they're not necessarily a bad thing, right? It's just how we talk. We need to think about the next thing we're going to say. But to some people, it might give the impression that you are not confident in what you're saying, right? So thanks to the power of movie magic, we can cut these vocal fillers out for cleaner, smoother takes. And I have a little demonstration here that I would like to show. Hopefully this works. If not, Victoria can come up here and help me out really quickly. Let's hope this works.
Just need to share which screen here.
Okay. I opened it in Safari. So. If it can't, I think it's in the background. Or no, I think that's just the screensaver. It's cut demo.
Okay.
It says it there. It's a good thing I'm going first so we can get this stuff out of the way.
Video.
It's just like a 30-second, less than 30-second little thing showing the power of a cut. But if we don't need it, and we can just keep moving forward.
Okay. If you're okay with
moving forward.
Yeah. Let's not complicate things. Color correction. So sometimes let me full screen this again just in case. Okay. So sorry about that, but let's talk about color correction. Sometimes the color of our clips is just off. It's not exactly how we want it to look sometimes, and that can throw people off. Cameras usually when you get footage from any sort of source that is not processed footage. It's raw footage, right? And the color values of it can be modified in any sort of editing software afterwards. The RGB values, the hue. I'll talk all about it afterwards. But anyways, movie magic allows us to adjust things like brightness, saturation, and hue to enhance the look of our video clips. Now, unfortunately, actually, hold on. Let me. So hue, as I described, is basically just the color you're choosing, right? It's color, you're familiar with the rainbow. I don't have to describe it to you. Saturation is the intensity of those colors, right? How intense of a shade of red we're using, how intense of a shade of yellow or blue we're using. And brightness is pretty self-explanatory. It's how bright or how dark your clip is. Sometimes in certain situations, the brightness really is, in my opinion, one of the last things I want to adjust. It just looks a little off if you play with it too much in post. So ideally, if you're shooting anything, you want to shoot it in a place with even lighting. If you're shooting outside, you want it to be, what's the word for it? Overcast. Right? The biggest enemy when it comes to shooting any video outside is spotty lighting. Right? If you shoot in an area with a bunch of leaves where light kind of filters through and there's a bunch of different shadows on a person, that can be a headache to edit. It can be a little challenging. So unfortunately, I can't show examples, but don't worry about it. We're going to keep moving forward because the most important part of all of this is the interview. The art of the interview is the most important part, and the most important part of the interview are the questions you ask. So in order to ask good questions, research. You got to go into the interview knowing what the project is about. That's how you can ask informed questions. I always come into almost every interview with a list of questions I'm going to ask. But an important part of that is also not to adhere to that list 100%. And that's where active listening comes in. I see a lot of journalists. I work with a lot of journalists. And journalists have a tendency to, when someone is talking, they just they just nod their heads along, right? They're not really listening to what the person is saying. They're just thinking, I can't wait to ask my next question. You have to take a moment to actually listen to what the person is saying to you. If you aren't asking questions about things that you're not sure of, you are doing not only a disservice to yourself, but a disservice to the audience. You have to be actively listening. Also super important, especially if you're working in SciComm, don't be afraid to not know things. That's like the whole point. You're not supposed to know everything. And I think the most beautiful thing about it is that you are taking a concept that to many people is very complicated, very sort of shrouded in mystery, and making it simpler. You're making it easy to understand without necessarily butchering the complexity of it, right? I think that is super duper important. And of course, think about your audience. Think about who you're writing for. If you're writing for a general audience, what would they be interested in? What do they want to know about this project? Asking good questions is at the core of what science communicators do. So what's next? So I have a lot more to do before my time with IMSI is up. I plan on conducting my own interviews and editing the footage together, writing a feature on maybe one of your projects, and designing social media graphics to kick off IMSI social media presence. As I said, if you like the LinkedIn post, thank you, I love you. Oh, speaking of interviews, you all broke my heart because I sent out a whole lot of emails, and none of you answered them. Actually, one person answered. Shout out. So this is a schedule I have for you to follow. You can take a picture of that. If that's your project, I'd like to speak with you. So please take a picture of it. I will be lurking around here. If that time doesn't work for you, just let me know, and I can accommodate. I'm going to be here basically all day and all day tomorrow as well. But take a picture of that. Is that your yes?
Can we still sign up?
Yeah, sure. Go for it. Crazy. Yeah, go crazy. So this is just a go crazy, right? Have fun signing up for it. I'm only putting the schedule in here because no one signed up for it.
Yes.
Don't be nervous. I don't bite.
You have a captive audience, so it'll be easier to profess it.
Perfect. Yes, I was waiting to get all of you in the same room to corner you into this.
We're waiting to get in the same room so we could schedule with you in person.
Yes, exactly. I knew the email wasn't going to work. I was very, very aware of that. We also got Friday as well. A lot more interviews on Friday. I put so the time frames there are 20 minutes. It might be less if I'm being completely honest with you. It depends on how the interview goes. Might be less. I don't think it'll exceed 20 minutes, but if we have a really good conversation, who knows? So I would take a picture of that. Now, if you still want to schedule a time individually, you can still do that. Check your emails. I sent out links for the people who are going to be here in person. You can still schedule that. Boop. Things to consider before coming to the interview. How would you explain your project to a loved one who isn't a scientist or a researcher, right? If you reframe your project in that way, it makes it easier to sort of explain it in layman's terms, right? Because I'm not a researcher, but I can tell that researchers and scientists often get caught up with a lot of the jargon that they use, a lot of the scientific terms. And to some people, they're just not familiar with it, and it's confusing. So go into this like you're going to explain it to a loved one who is not a scientist. Actually, for journalism, we're taught to write at a fifth grade reading level for almost everything we do. It's just easier to understand. It's not demeaning. It's not dumbing things down. I don't like that term, dumbing things down, by the way. I prefer just simplifying things. So, also, this is kind of cheating. This is one of the things I'll be asking you. What will be the impact of your findings? Think about what your project is going to do. What will be the impact? And any fun stories or anecdotes related to your project, those make for great content. Those make for great B-roll. Any of that is phenomenal. Also, speaking of B-roll, which I previously explained, if you have any sort of footage or photos of your project, that's great too. Please send that to me, because that'll go in the video. I'll credit you. It'll be lovely. And I'd like to know a little bit more about yourself. Why were you interested in this project? What brought you into this? Because as much as I care about learning about what your project is, I want to know more about you as well. The researcher. Why does this interest you? Why movement science? Why biomechanics? Why all of this? And finally, don't be super nervous. I will walk you through the interview process. There's nothing to be nervous about. If you mess up, you can just start again. There is no pressure there. I just want to learn more about you and your project. So don't be nervous. All right? I don't bite.
And we have editing magic.
And we have movie magic to make you sound even smarter than you all already are. So personal takeaways. This project has reinforced my belief that science communication is integral to any society. Being able to communicate what you do to people in a way they can actually understand is a valuable skill. And I like this bullet point because I thought about this. It's really not about knowing everything. It's about knowing that you don't know everything. When you acknowledge the fact you don't know everything, you open yourself up to a whole lot more possibilities. You ask better questions. You take a more personal interest in science. It's about learning things. Science evolves, it changes. It's a body of information that changes with time. It's about learning. Thank you all for this wonderful opportunity. I don't know how fast I went. If anyone wants to ask questions, I don't know if I have time for questions, do I?
We can maybe give you one question, and everybody's going to talk to you this afternoon, Friday.
Yes.
So you guys will have a chance.
Well, we have a coffee break scheduled right now, and I was thinking we can shorten that so that we can get back on track. So we could still take a couple minutes for questions if people have burning questions.
Anyone have any questions?
While people were asking questions, I just want to point out, so the live stream is up, I posted it. I posted it a little bit in detail.
Brian edited together based on terrible raw footage that I collected. That he said he's added to the outreach part of this project, so go check those out during the break.
Thank you so much. If no more questions, then I'm good. Thank you all. Seriously. Oh,
You don't have a question, but I have a comment. Oh, did I? Yeah.
No.
I just want to say, I think like at this moment in time, this is so important to communicate the value of what we do to, that portion of society who doesn't know. And so I really think that it's wonderful that you and Christian are doing this for us. And I do think that we should engage. So thank you.
Thank you. I think it's very absolutely. Anyone else? Any comments on the Zoom?
That was really useful information to share. So I don't have questions, but I just want to say I really appreciate it. I think it's really good for the team to think about these things and make science communication just part of our everyday practice.
If you have time later, we'd want to see those movie magic clips that you weren't able to show.
I think we're going to share this link in Slack. So
Yeah. I would love to show you. Yes, I had really nice demonstrations of like me cutting out ums and buts and all that, and color correction, which looked really nice. Shame I couldn't share it, but we got through it.
Share it on the Slack, so it will be available to everybody.
Yeah. It's sweet. And we'll probably share the YouTube videos to the Slack too.
Yeah.
We'll get them. Okay. All right. Thank you, everyone.
Yeah, so we have 8 minutes before the scheduled start of the next topic, right?
Yeah. 8-minute break.
So take 6 minutes and then we will get back in.
Well, I'm Cody. I'm a student here at UCI. I'm a rising fourth year biosci major. My project was P20, focusing on human balance and developing capacity tests to see how that might affect how people balance. This test was focusing on tandem balance in different people. Tandem balance would be when you're walking on, for example, a tightrope where you have one foot placed in front of the other and you're trying to maintain balance, yeah. We came to a few conclusions from the study. We found that, for example, ankle proprioception is extremely important, so being aware of how, when you place your foot, where it's going to be, your ability to maintain stable ankle.
My name is Leah Houston. I am from Cal State Fullerton, and I'm a kinesiology student minoring in aging research. I worked with the amazing Dr. James Finley in the USC Locomotor Control Lab, where we worked on perturbations and how it affected our proactive and reactive balance control strategies. What we did in the lab was trip ourselves and trip others. So that also included putting markers on different parts of the body and motion capture with different programs like Visual 3D, QTM, all sorts of different programs. What I learned from tripping people is that there is a funnel effect where we can look at the leg, what is happening at the leg, kinematic, kinetic forces. Then we can look at the joint and dive into muscle activation and timing and everything like that. Potential future direction for this work is utilizing EMG to locate and identify what muscles are working in proactive versus reactive balance control strategies. The best part about doing the IMSI research was finding who I am. I have never felt more myself, being independent, learning confidence. I just grew so much as a person in both the lab and in life.
It is. Kind of. It is. It's just. It is directional, so if you can make it go right, it will work. Yeah. Cool.
Like this?
Yeah.
Like it? Like it?
Yeah, I think so. Yep. All right, welcome back, everyone. If you can hear us, we're joining back in person here. So I'm gonna let you take it away.
All right. Well, Vanson's actually starting first. Can you guys see him?
Oh, I think he needs
Hello?
to turn on his videos.
Hello.
Video's on.
Oh,
Can you guys hear me?
yeah. You just have. Yeah.
Hello. Okay. Hi everyone. My name is Vanson Vu. I'm a second year undergrad at Brown University, and I was really excited to be a part of the IMSI Summer Institute this past summer.
Hi, my name is Emma Blaylock, and I'm going to be a senior undergraduate here at the University of California, Irvine. And our project is Sensing in Motion, Perturbing Proprioceptive Feedback and Dynamic Tap.
So our project centers around proprioceptors, which are sensory receptors that provide the body with information and feedback about position and movement. We specifically focus on muscle spindles since they are the primary proprioceptors for sensing body position and controlling motor coordination. They do this through detecting the stretch or change in length of the muscle and relaying that information to the central nervous system. Because of the important role they play in precise movement control and body position, muscle spindles are often the target for studies that examine the effects of focal muscle vibration. Aiming to enhance or alter movement through specific spindle activation, most of these studies use focal muscle vibration for a therapeutic purpose. For example, Lee et al. Had chronic stroke patients take part in weight-bearing and weight-shifting training while focal muscle vibration was applied to their ankle and foot. After a 6-week period of performing the training 5 days a week, patients showed significant gait improvements, specifically reducing postural sway and increasing step length. Additionally, Palloni et al. Also showed positive effects of focal muscle vibration on chronic stroke patients, specifically focusing on dorsiflexion. With vibration motors applied to the tibialis anterior, patients underwent general physical therapy 12 times over a 4-week period, which led to increased maximum dorsiflexion and higher tibialis anterior activation during the swing phase of gait. However, although these studies show positive signs for focal muscle vibrations enhancement of movement and motor control, they, like most past studies on the topic, use the stimulation as rehabilitation training with after effects observed later, which leaves a lack of evidence of the effect when applied simultaneously with dynamic motor activities. The literature is also still unclear as to how focal muscle vibration physiologically causes the effects seen in these studies, since the vibration could either be instantly enhancing proprioception or it could be disturbing and diminishing proprioception during the training phase, eventually leading the body to become more accurate through adaptation to the challenge. Due to these uncertainties in the literature, and in order to better understand how focal muscle vibration alters muscle movement when applied simultaneously in dynamic settings, we developed a 3-pronged experimental approach, starting with the reflex test, which involves no central nervous system input, then scaling up to the ankle proprioception test with monojointed motion, and lastly to the hopping task, which consists of multi-jointed motion. This hierarchical scale of proprioceptive dynamic tasks allowed us to examine the effects of focal muscle vibration across increasing levels of complexity, hopefully giving us a clear understanding of the physiological mechanism driving the vibration's positive effects. Up here is also a diagram of the focal muscle vibration motors we use. These small metal disc-shaped ends were placed on the skin, and we were able to switch them on to provide localized vibration to the muscle. In the patellar tendon reflex test, we placed an EMG on the rectus femoris to measure muscle activity, an IMU on the knee to measure the exact timing of the tendon tap, an IMU on the ankle to track the magnitude of the reflex response, and for the vibration conditions, 3 motors on the rectus femoris. We then had the participant close their eyes and rest their leg on a wooden plank to keep it still. After randomizing between starting with the vibration or the control, we executed 3 successful taps with the reflex hammer for each of the 2 conditions. Our goal for this test was to extract the timing delay between the elicitation of the reflex and the muscle response, and compare the response timing with and without vibration. And then we also have a quick video clip of Emma performing the reflex test with the motors turned on. These graphs here show the data we extracted. The top left graph is the accelerometer data from the IMU on the knee. The middle left graph is the rectus femoris EMG signal, and the bottom and right graphs show them overlaid with the start of the reflex marked in green where the accelerometer data crosses the threshold, and the peak muscle activation also marked in green. We defined stretch reflex muscle latency as the time difference between these 2 green points. And then these graphs on the left show each individual participant's latency time with the vibration condition compared to the control condition. Then on the right is all participants combined onto one plot. Preliminary results showed that both group and individual latency between conditions was insignificant, with only participant 3 showing some potential effect. There was also much more variance in the vibration conditions compared to the control, which we believe could be a potential effect from the vibration. In future trials, we hope to get more consistent with our taps, since we wasted a lot of time on unsuccessful taps that didn't elicit any response. This would allow us to collect more taps per condition and reduce variability, which would help us confirm whether or not there is truly an effect from the vibration. For the ankle proprioception test, we utilized the AMPD controller in the rehabilitation and augmentation lab. As you can see in the diagram here, the controller has the participant seated with their ankles strapped to 2 pedals with a board preventing them from seeing their lower body. The controller can run a variety of tests, but for our study's purpose, we focused on one called crisscross. In crisscross, the participants' feet are mechanically moved in opposite directions through plantar flexion and dorsiflexion. And once they sense when their feet are aligned, they press a button and the controller records the accuracy of their detection. This graph here is an example of what the controller outputs, with the actual cross and the participant's perceived cross marked with the red vertical lines. And then the difference between these 2 positions is extracted in degrees as the error. And then here we have an example video of the participant performing crisscross. You can see the machine moving the feet in opposite directions. And then once the participant feels that their feet are aligned, they press that red button near the top. And this will repeat several times per trial at varying speeds and crossing positions.
All right. Is my mic working?
Yeah.
All right. This is the preliminary results from our
AMPD controller test. All testing was performed on the dominant leg, and positional error was calculated during phases. And the target muscle group was lengthening as a result of the AMPD crisscross task. Vibration was applied either to the tibialis anterior or to the soleus during these trials, and each had its own corresponding control condition with no vibration applied. For data visualization, the y-axis represents positional error measured in degrees, while the x-axis represents the condition. Each dotted point corresponds to a single crisscross trial, pairing one participant with one condition. We use a Crushall-Wallace test followed by Mann-Whitney U comparisons to analyze differences across conditions. With our current sample size of 3 participants, we did not see consistent group-wide improvements in joint position sensing with focal muscle vibration compared to control. When looking at pairwise comparisons, neither the TA or soleus vibration conditions differed significantly from their respective controls. However, there was a significant difference when comparing TA and soleus directly, as well as when comparing their control conditions. This suggests that vibration effects may vary depending on the muscle group targeted, but with such a small sample size, these findings should be interpreted cautiously. More participants will help clarify whether these trends hold at a larger scale. One potential flaw in our design is that we do not factor in movement speed, despite the strong relationship between spindle activity and velocity. Primary spindle endings are highly sensitive to dynamic velocity changes, while secondary endings respond more to static length. By not accounting for speed, we may have overlooked an important variable that influences how spindles respond during lengthening. This slide highlights why we tested at the extremes of plantar flexion and dorsiflexion. At these end ranges, joint proprioceptors are most active in sensing position. To assess this, we evaluated positional error between 80% plantar flexion and dorsiflexion, since that's where the proprioceptive feedback is most reliable. As this graph displays, the y-axis represents mean absolute error in degrees, while the x-axis shows the normalized crossing position expressed as a percentage. This figure shows mean positional error across the dominant leg's full range of motion, from plantar flexion on the left to dorsiflexion on the right. Each colored line corresponds to a specific condition. The red represents the vibration on the soleus, the green represents the vibration on the tibialis anterior, the blue is the controlled soleus, and the purple represents the control for the tibialis. When comparing vibration conditions to their control counterparts, we didn't find any significant differences within or between quartiles. All p-values were greater than 0.05. In other words, vibration did not systematically improve or worsen joint position sensing across the range of motion in this preliminary data set. In this experiment, we examined how focal muscle vibration alters muscle spindle sensitivity and affects leg stiffness during dynamic hopping. Each participant's body weight was first measured in order to calculate 20% of their body mass, which determined the load for the weighted vest condition. Participants then completed hopping under 4 main states: without weight, with a weighted vest, with motors, and then with the weighted vest and motors. Within each state, they performed 3 trials: a static calibration with 30 seconds of natural hopping, followed by hopping to a metronome set at frequencies 10% higher and 10% lower than their natural rate. Throughout all trials, motion capture, EMG, and force plates were used to track movement, muscle activity, and ground reaction forces. This design gave us 12 total conditions. Importantly, it allowed us to make 2 direct comparisons. First, between the control condition without weight and motors and the motor on condition to isolate the effect of vibration alone. And second, between the weighted vest condition with motors off and the weighted vest condition with motors on to determine how vibration influences hopping mechanics under added load. These comparisons provided a clear way to examine how both weight and focal muscle vibration interact to affect lower limb mechanics and proprioceptive control. For the hopping task, we placed 7 EMG electrodes on specific muscles, and the numbering remained constant across all participants. On electrode 1, we have on the tibialis anterior. 2 is on the soleus, 3 is on the medial gastrocnemius, 4 on the vastus lateralis, 5 on the vastus medialis, 6 on the rectus femoris, and 7 on the biceps femoris.
Here we have an image of a participant wearing the weighted vest, with all EMG electrodes wrapped securely to prevent any movement, and you can see the motion capture markers also placed according to the Vicon Nexus plug-in gate lower body model. Next to the image is a video, which I'm going to go back to replay. This person, the same participant that's on the left, is hopping at a frequency 10% higher without motors or without a weighted vest. I'll let the video play and then I'll explain it. Okay. The video features the same participant shown previously, with markers moving in 3D space and the EMG signals reflecting the muscle activations during hopping. So I'll replay that again so that you guys can see both. All right. Here we looked at leg stiffness during hopping, comparing control to vibration. We measured stiffness from hip displacement relative to peak ground force. Each graph represents one individual, starting with SO2 on the left to SO4 on the right. The y-axis displays leg stiffness in newtons per meter, while the x-axis displays a condition of control versus vibration. The three lines represent the different hopping frequencies. What stands out is that people respond differently. Some increase stiffness with vibration while others decrease. So vibration doesn't have one uniform effect, but rather shows a lot of individual variability. Here we have the preliminary results for the hopping task. Positional displacement was defined by calculating the 80% ellipse area based on the center of pressure position at landing. This method captures the spread of the landing points in both the medial lateral direction, shown on the y-axis, the x-axis, and on the y-axis is the anterior-posterior position. The graph on the right shows the ellipse area by group with individual data points. The y-axis represents the normalized ellipse area, while the x-axis increasing the sample size to improve statistical power and confirm whether the trends we find the experimental design by testing different vibration frequencies and durations while controlling for learning and fatigue effects. Another key step will be analyzing individual variability to identify why some participants respond differently than others. And then finally, we want to expand more to functional tasks like walking or balance, and even more long-term effects to see if repeated vibration training can lead to lasting improvements in proprioception. So this is my slide of what I learned. Other than all these techniques that I learned, I mostly learned how to have fun in research. I'm a type of person to kind of focus on getting the project done and not the process. So this is actually a video of Lauren just having fun in the 3D space. I really enjoyed that video. And I really enjoyed getting to meet everyone at IMSI. And then this next slide is for Vanson.
Yep, and then for my takeaways, this was my very first research experience, so it was a really great introduction to not only the field, but also just collaborating in science in general with my peers and mentors, which was a lot of fun as well. And I also learned a lot about how to code in MATLAB and process data, which was super interesting and will also be super useful going forward as we continue our project and also for future projects down the road, hopefully.
Thank you, Vanson. And then this is just a thank you to everyone else who contributed to our project other than Vanson and I, the undergraduate students. So that's it. Making a lot of noise. Okay.
Great. We have some time for some questions.
Oh yeah. So how do you quantify the strength of the vibration?
That is a very good question for Lauren behind you. I'm not sure how to answer that.
So the strength of the vibration is usually based on battery. So the voltage that the battery is giving to the vibrators. We had them around the same voltage across all participants. So on the spec sheet, I think it corresponds to a certain amplitude and a certain frequency. And those are
because it's an amplitude.
We had the two motors, Lauren, right? For one we use on the AMPD, we had really big motors, and then the ones we use, the smaller ones, although those got really hot really fast. So that might also be an issue that we had to take them off of people and then put them back on.
Yeah, because maybe if you could see how strong the vibration was in those papers, maybe you have to try to match that.
Just some of the really sophisticated tendon vibrators have a control of natural force.
Either they have a pressure sensor or a force sensor.
You can have a feedback loop that like tells force, or you can at least have a sensor to give you the force, but those cheap sensors don't usually have the bandwidth to give it the vibration. And then the other one you could think about measuring is the force of the tap. But that's always the challenge for the twin vibration.
Getting it all of those things consistent across.
Yeah, so we don't have this like pendulum device, but then doesn't always hit right. So it's a challenge.
Any other questions?
We've got one online.
Okay. Vanson can answer the online one.
What was the question?
I think he needs to ask
I didn't
it.
hear.
He's gonna ask it, I think.
Okay.
For James.
Oh, now I can hear. Yeah, so I think a lot of the sort of literature on vibration and proprioception, they target the tendon. So using various types of vibratory motors or things that directly, stretch the muscle. So I was wondering if you all have considered applying the motors maybe directly to the patellar tendon, because I've done these, tried these things out, and they generate really large perceptual distortions, like the perception that your limb is moving. So I wonder if you could talk a little bit about the choice to stimulate at the muscle versus the tendon.
Yeah, we were just more curious about like the muscle activation more so than like actually at the site of the like sense of the reflex, more so like the reflex arc and like the timing of that and the latency of that.
Yeah, I think it'd be interesting to see if you applied those motors directly to the patellar tendon and just left them on for a while. If people close their eyes, if they get a sensation of movement, that's one of the sort of common perceptions that you see in tendon vibration studies.
Yeah, that would definitely be interesting to look at. Yeah.
All right. Well, thank you so much, Team Sensing in Motion. Yeah, there's another question in the chat, but just to make sure that we stay on time, since we have a few presentations, please just follow up with this team afterwards. All right. Thank you.
It's left.
Yeah.
But I thought so was, I need to do the series.
Hi, my name's Chloe. My name's Lauren, and we're from the Tension and Motion group. Our project is about actuating in situ muscle tendon preparations using in vivo dynamics derived from tissue and joint organization methods. So a central challenge in biomechanics is capturing just how muscle tendon units actually behave. When we talk about muscle tendon dynamics, we're referring to the complex changes in both length and force development generated during locomotor activity. So this is a complex process in itself that encompasses changes in both feed forward and feedback mechanisms that can modulate.
In propel, so it's in one place. Thank you. Yeah.
It can modulate outcomes. So muscles are a hierarchical structural system scaled down from sarcomeres all the way up to muscle fibers itself. Simultaneously, while looking at the whole body system, this is a hierarchical neuromechanical structure that defines whole body behavior. And these two systems exclude at the point of
Yeah, just put your mouse over the, yeah.
At MTU. So given that MTU dynamics have such a vital role in determining locomotor behavior and performance, our current methods of estimating MTU lengths must be rigorously tested and validated. Our project itself was interested in designing a methodological approach that would systematically and in a complex, controlled manner test common approaches to estimating MTU length and specifically testing the sensitivity of our assumptions made when constructing our estimates.
So we're going to orient the audience to two general common approaches that.
If you can flip the mic to your shirt, it produces a more consistent sound. Sorry.
To two general common approaches that many researchers in the field take in estimating MTU trajectories. The first one that we'll review is from the joint level. And this incorporates measurements of joint angles and moment arms. Some of the pros to this approach is its feasibility across species. It's easy to set up a camera in front of any species or any animal and just videotape them in their natural environment. As well as it's a non-invasive approach, meaning that the movements or mechanics that you see on the video are pretty similar to the movements and mechanics that you would expect to see in their natural terrain or in their environment. Some of the limitations, though, to this approach is its assumption of a generic muscle tendon architecture. We tend to assume that the muscle is a parallel fibered muscle and the series compliant element is not necessarily as compliant as maybe it is in actuality. As well as we tend to miss key information sometimes on dynamics of moment arms. We know that the articulations between two joints and as they're changing relative to one another can alter the joint center. And so when we assume static moment arms, sometimes we can miss information about the actual forces that are being developed in our system, as well as these estimations are very sensitive to the tracking and the algorithms that you use, whether they're manual or machine-based. In general, this approach is super feasible, but it doesn't really provide a deep resolution of what's happening on the MTU level. The second common approach that many people take is from a tissue level. So if we zoom in and we look specifically at the muscle itself, these approaches tend to take measurements of muscle fascicle length, muscle force from tendon deformation, and muscle activation from EMG, and combine these measurements in a very direct and methodological way in order to really get a sense of what the muscle is doing during the movement. This can be very targeted and species specific, so you can get a real sense of what the muscle behavior is during the locomotor behavior. Some of the limitations, though, to this approach is it's invasive. It can be technically challenging to synchronize all these various devices in line with each other, as we found that out during the summer. And there's an inherent bias in the muscles that are sampled. Using this approach, you really have to use muscles that are superficial and that are really accessible. So in the literature, it tends to be a conglomeration of just those specific muscles, though we know there's a diversity of muscles that are actually working to augment the movement, but the limitation is we can only access certain ones. This method also assumes and very much simplifies fascicle dynamics, very much so that we know there's regional differences across the muscle belly in the way that fascicle strain and tendon compliance and also time varying pennation angles, in which we don't really capture that using this approach. It does give us a finer resolution of maybe the dynamics, but it does oversimplify some of the important mechanical aspects of the system, and it's very tissue and species sensitive. So neither approach is perfect, as we've seen from Lauren. Both approaches definitely make their own assumptions about the muscle tendon unit that aren't really captured quantitatively. So muscles don't just shorten and lengthen like springs, they're actually responding dynamically. They depend on architecture, history dependence, and even activation timing. So accurate estimates are really essential for scaling across species, modeling locomotion, and validating simulation frameworks. By comparing these approaches to characterize MTU dynamics and replaying predictions, into an controlled in situ prep, we can definitely evaluate the validity of these estimations and assumptions. The two questions we're trying to answer with this approach are, how do these approaches vary in practice? And do these approaches accurately describe in vivo dynamics itself? So we chose guinea fowl from a data set because they are both trainable and they have similar bipedal dynamics to humans themselves. We collected lateral gastrocnemius tissue and joint level data from running guinea fowl, and we use in vivo joint level and tissue level measurements to estimate MTU length. So what we have is some of our in vivo data. It's broken up into strides. So what you're seeing is the combination of both the swing and stance phase of our both our kinematics and our tissue level measurements. What you see is two trajectories. Both are color coordinated in purple and in green. And these are specific, more or less clusters of our in vivo data set. There's a variation inherently in our data set that we had. And we found two general clusters that kind of were defined based on differences in specific muscle function, which if we take a look at our force and our velocity, the two groups were very distinct in terms of the peak force and peak velocities that they achieved. So we were able to distinguish two separate groups, and then we pulled both their groupings for the tissue level and for the joint level. Using some of our kinematic data, we were able to use the joint angles in our MTU estimates for our joint level approach. And then we're also able to incorporate our fascicle lengths into our tissue level approaches. So just to make sure everyone's oriented on the same page, because we do go through a few colors, we represent both purple and green are in vivo trajectories that we will be taking joint level and tissue level estimates from the two. So we'll go over the equations for our estimates. First, for our joint level, we take static moment arms at both the ankle and the knee, as well as the change in joint angle at both of those joints. And we incorporate a MTU reference length. And so this is an anatomical reference length of the MTU that corresponds to a fascicle optimal length. And then for our equation for our tissue level estimates, we use fascicle length, the static pennation angle, and a tendon length to estimate the MTU trajectory for our tissue level estimates. And these are the two output trajectories that we were able to get for MTUs. And what we can see on the top is going to be our joint level coming from both that purple and green in vivo trajectories. And then on the bottom is our tissue level for both the purple and green trajectories of our in vivo data. And what we can see distinctly is these are different. The amplitude and the strains are somewhat similar, but they do vary a bit. And as well as you can see that period that I've pointed out, there is variation between how the tissue level approach, joint level approach and the tissue level approach approximated the MTU trajectories, both in distinct ways. And what we would hypothesize is if we're going from A to B and C to B, we would land on the same thing. But in reality, we actually don't, which we could hypothesize that there's something within our assumptions that are maybe leading us to have different results between the two approach strategies. So our first question, how do these approaches vary? Well, they do, and they vary in both amplitude and strain. So just going over our in situ prep in general, first we anesthetize the bird and lay it on its side on this table before we open its leg near the rear to isolate the sciatic nerve and sever it from the central nervous system. And then we add the nerve cuff to send nerve stimulations before the leg is rigidly secured to the table, and the lateral gastrocnemius muscle is attached to this ergometer lever. And we also instrument for sonomicrometry crystals into the LG muscle. And then we get our inputs from MTU length and activation pattern.
and we receive outputs of muscle force, fascicle length, and muscle thickness. All inputs are being sent to our setup using our modulate, and we construct a force length curve of the MTU and then select MTU length that corresponds to the highest active force. We use the MTU length to then normalize all of our data for each individual bird's reference length.
So now once we've found the reference length for our MTU, we can now play in our estimated trajectories into that system. And so we can simultaneously record both the total MTU length, we can measure our fascicle, and we can measure our force, and then we can end up computing our velocity. And what we did is we compared those estimates from our in situ controlled prep to our in vivo trajectories that we got. So just as a reminder, our purple and our green are those distinct in vivo trajectories. And then our two estimate strategies for both of them are in the blue and the orange. And we'll go through each of them together. Just explaining some of the differences that we found in our preliminary data and then some of the decisions that we're making going forward with our approach. So what we can see initially is a initial length offset between what we saw in vivo and then what we measured in situ, as well as we actually had a pretty similar strain relationship between the two estimates themselves and then the estimates and the actual in vivo trajectories. For our force, we can see that there was a slight delay in our force timing. And then because we were doing our in situ preps at maximally stimulated intensities, we also see that the amplitudes between our estimates and our in vivo trajectories were slightly offset as well. And then in terms of our velocity, we can see very similar patterns in terms of fascicle strain rates, even though there was a slight offset in that, about 5 milliseconds. So what we took away from our initial pilot data and have implemented into our new approaches is defining really the nuances and the differences between in vivo data, in vivo neuromechanical delays, and in situ neuromechanical delays to really get our force delay shifted more towards the right, and so those forces line up. We have also been considering potentially submaximally stimulating our in situ preps to be more representative of the actual activation levels that we see during dynamic locomotion, and as well as constructing ways to maybe get around this fascicle length offset despite our MTU offset being pretty much 0 as well. So to answer our second question of do these approaches accurately describe our in vivo patterns, sort of. We see some similarities between especially during the velocities, but we still have some fine tuning and refinement for our protocols to accurately depict both the fascicle and the force. So we're also collecting unsteady and perturbed in vivo jumping data, one with a swinging perch at various heights and another at added mass to the bird at a constant height. And both have instrumented LG and digital flexor 3 muscles using EMG crystals, using EMG sonomicrometry crystals and buckles. So these are just 2 sample videos that we collected. On the right side, we have a slow, like a fast stabilization strategy, while the left side is a slow stabilization strategy. You can see on the fast side, he has a very, the only side is playing. Okay. The slow side, you can see he's using his wings to very much stabilize himself on the swing, but the swing is also slightly moving, showing a slower stabilization strategy. While the fast side, the bird almost immediately settles on the swing with little to no swing movement. Okay, so just our next steps for our project, just more tasks, more muscles, more everything, just so we can make our experiments just more similar to human protocols itself.
And just a huge thanks to our near peer mentor, Dr. Bemis, and our 2 project advisors, Dr. Daly and Dr. Azizi. And big shout out to Wayne from Sonometrics for all his help. Any questions? Any questions?
We have a couple minutes for questions.
Why do you think there was such a big delay in the forest? Is it actually transmitting through the tissues slower?
We do know there's like a length dependence on the activation, so we tried to untangle whether it was because of that or because, you know, there's different timing relationships when you have an in situ prep versus when you actually have the whole system interconnected. What we think we've determined is we just needed to refine a little bit better our timing in relationship to our EMGs that we had in situ, and then account for a slight offset that we saw in our in situ preps, which was like around 8 milliseconds. We're still looking into the actual factors that are causing that delay, but we do believe that we've timed it out right now going forward in our future preps.
We want to know what you think, Lena.
Yeah, so like, this is a surprise to us how big that delay was.
Is there something fundamentally different between in vivo and artificially stimulating the nerve?
Yes, no, I mean, it's the ongoing length change.
Threshold.
So there's some very nice papers on this. So the canonical delays that we have isometrically don't apply when the muscle is changing length.
Mm-hmm.
And so a shortening muscle can have a EC coupling delay of 120 milliseconds. And a lengthening muscle can have an EC delay of 5 milliseconds. And there's a nice paper by Patrick Crago on this, and there's a nice paper from CJ Heckman and Tom Sandercock. And we need to, you know, like, I think in our benchtop paper, this is one of the things that we really want to address, that these things you measure isometrically don't apply to dynamic movement. And that's one of the reasons why we've been optimizing the activation in our avatar experiments.
We talked about also looking at our in vivo data for these measurements too. So we can look at the delay between peak MG and peak force.
Yeah.
Like, and how that varies under different conditions, and hopefully get a range of what that delay is and see how it compares to this prep.
Yeah, we have some initial measurements that show that it seems to be decently consistent when we do our trajectories, but there is slight variation within that, even as we either activate it during the stretch and then shorten, or when we only activate when we're shortening.
So we did shift the length trajectories so that they're not shortening immediately and then being stimulated because of that.
So it kind of depends on what you were doing with the muscle in the prep right before you stimulated.
Yeah. So there's like
you have to put it, you almost have to put it through a passive trajectory that matches in vivo first before you do.
Yeah.
And the nature of activation is very binary in the in situ case, where it's off and then it's on.
Right.
Whereas the nervous system ramps up that level of activation, and so that could also.
You also have recruitment, right? So
That's another factor.
you know, you're activating fast muscle fibers first, which might
You'd think that would shorten. Yeah, I would think rather than increase it.
Yeah.
that would be on.
Create more problems for it, Lena.
Well, but the delay is longer in situ, even though we should be recruiting fast.
I got it
fibers. So,
backwards.
yeah, it's like.
Yeah, but we aren't accounting for the differences between the in situ and the in vivo, right? So in the avatar, we moved at 26 milliseconds up, you know, because we were stimulating like whole field, but we didn't account for that originally because there were so many things we were trying to integrate.
So
Sorry to interrupt this discussion. It's a great one. Going with this. All right. Our next presentation is going to be virtual. Bonde is joining us from Georgia Tech today. If you're ready to share your screen, you can go ahead and do so. Bonde, if you are online. Yes.
We still can barely hear you, Victoria.
Still can barely hear me. Okay. Well, you don't need to hear me too much.
Wait, are you hearing the other speakers okay, Simon?
Yeah, you're loud and clear, Monica. I think it's the mic that Victoria's holding isn't working.
I think it's because there's some delay in the directional mic in this room, and so once the audience shuts up for a minute, it will readjust.
Okay. I'll project a little bit for now so that you can hear me from the mic. But Bonde, when you're ready, please go ahead and share your screen.
You could type it in the chat too, maybe.
Yeah. Oh, there she is. Okay.
Okay, hi, can everyone hear me okay?
Yeah.
Yeah, we can hear you.
Perfect. All right. Awesome. So I am Olubande Taiwo. I'm a Georgia Tech student, and this summer I was under the direction of postdoc Ethan Wold and Professor Simon Sponberg, studying bee perturbation. So winged animals are required to fly at really high speeds through their cluttered environments. They may come into contact with obstacles such as wind, rain, or vegetation. As you can see, these bee flies are quickly navigating around their environment. And although they do have an efficient way of doing that, they still come into contact with obstacles. So we wanted to specifically study what happens when they do. As you can see on the video on the right, this is a bumblebee coming into contact with fishing wire. So it's a bit hard to see, but there's that vertical line and the bee hits it and the wing stops almost instantaneously, which is something that suggests that it's faster than the neural drive that would allow them to do so, because it is like within a few seconds the wing stops. So the neural drive that would cause that wing to stop is not quite that fast in order to have that happen. So this suggests that asynchronous flight has something to do with it. In animals such as moths, they fly synchronously, which means that each neural drive will impact their wing motion. So with every neural drive, it is accompanied by a wing motion. But in animals such as bees that fly asynchronously, their flight is might be motivated by a neural drive that causes the muscle to stretch, and then it automatically generates the wing beats, which allows them to fly faster than if every wing beat was generated by a neural drive, such as in a synchronous system. So in this experiment, an asynchronous wing muscle was isolated and stretched. And as you can see, the force then allows the wing to create its own force afterwards. So there are two muscles involved in bee flight and indirect flight muscles. There's the DVM and the DLM, and they're basically taking turns contracting and stretching due to the force. So our hypothesis based on this information was that if bees can stop their wings post-collision without direct action from the nervous system, their wing oscillation should stop within approximately 3 wing strokes, because that would be faster than the neural drive would tell them to stop their wings. And additionally, if the wing stop phenomenon is a result of the delayed stretch activation, wing collision interaction should be quicker when observed within the mid-stroke phase ranges. So we began data acquisition pretty early on in the semester. We've constructed an arena that consisted of the hive on one side, and the flight chamber itself had an obstacle apparatus consisting of fishing wire, like that initial video you saw. It was about a 2x3 array or 2x5 array of fishing wire across the middle of the arena, and then connecting to a foraging chamber on the right to motivate the bees to fly from their hive through the arena. So we observed the bees and recorded videos manually with the high-speed camera that you see on the top, and we collected data that way, anticipating them colliding with the wings as we observe the bees flying. So this is an example of a high-speed video that we collected. The frame rate is 5,000 frames per second. As you can see, the bee is colliding with the fishing wire with its left wing on the downstroke. So we really wanted to see what happened after that. So you can see that the bee is trying some to get to the recovery, and that is really what we're measuring, is the phenomenon of it colliding and then recovering immediately after. So we digitized using this MATLAB program, and we tracked the edges of each wing, left and right. We noted which one collided, and we observed other things about the wing strokes, as well as the frames that we digitized. We also digitized the thorax, that we would have a reference point to create that neat little graph that you see on the left. Across the 4 hives that we used in the fall and spring semesters, we digitized about 62 videos of 96 viable videos. So any videos in which it was blurry or inconsistencies with the plane of the bee's wing, we scrapped from data. So this is an example of the collision plot. This is actually the exact collision plot that is a result of the video that I showed earlier, of the high-speed video that we captured. So as you can see, that green vertical line represents the collision frame. And like I said earlier, it was collected with a frame rate of 5,000 frames per second. And you can see that that left wing, which is the blue, takes about 3 to 4 wing strokes to fully recover to its initial flight pattern. And that's what we initially hypothesized, was that within 3 wing strokes, it will recover to its initial pattern. In this, we estimated the time to rest. So one wing oscillation is approximately 5 milliseconds. So 15 milliseconds is about 3 wing oscillations. And as you can see, that vertical line representing 15 milliseconds, a lot of the population of points is before that. So it takes about 3 wing strokes for the wing to recover to its full pattern that was observed pre-collision. So the upstroke is represented by the 0.7 to 0.9 phase range, and there's a lot of population there as well. And the downstroke is represented from the 0.2 to 0.4 phase range. So going back to the hypothesis, if bees can stop their wings post-collision without direct action from the nervous system, the ring oscillation should stop within approximately 3 wing strokes. This was observed because collision responses are property of delayed stretch activation. So as I mentioned earlier, the 3 ring strokes that it takes, if it's within, if the product of the delayed stretch activation allows the wing to respond to perturbations immediately, then it will not require a nervous system impulse. So this is a distribution of the collision phase across, of collisions across the phase based on the change in wing beat amplitude. So we measured the wing beat amplitude pre and post collision, and then we graphed it simultaneously with the upstroke representing 0 to 0.5, and then the reversal of that 0.5 to back to 0 is the downstroke. So graphing those simultaneously, you can see mid-stroke, about 0.25 on the collision phase, there's a lot of population of points, which further demonstrates that when the muscle is stretched the most in the mid-stroke, it will have the most immediate and impactful response to a perturbation. And that is populated within all of those points that you see around that middle area. So that answers our second question. Additionally, if the wing stop phenomenon is a result of the delayed stretch activation, wing collision interaction should be quicker when observed within mid-stroke phase ranges. So yes, the middle ranges of up and down strokes yield the most impactful response in wing beat amplitude as the muscle is being actively stretched when it is in the mid-stroke of the up or down stroke. So this data allows us to estimate that there is a correlation between collision phase and the likelihood of the bee's wings stopping instantaneously. Although we don't have statistical, we don't have a statistical direction in order to determine if it's significant, there is a pattern being observed. So in the future, this project could benefit from a tethered bee experiment in which we measure force dissipation as a result of collision, like we did in the isolated asynchronous muscle experiment that I demonstrated earlier. So I just want to acknowledge NSF DBI for funding this project throughout the summer. Drew Whitson, Leo Liu, and Atika Kahale for data acquisition in the preliminary stages of the vertically integrated project in its early stages. So I definitely want to thank them for helping with basically over half of those videos. And thank you so much for listening to my presentation. I can take questions.
I don't know if you guys can hear me now, but if there are any questions in the room or online, please feel free to ask them.
I have like maybe a stupidish question. What view were we looking at when they were flying? Right? Because it seemed I couldn't quite tell what direction they were flying. Were we looking from above?
Yes. So in the recording, the camera is from top down. So the plane is like flat above them. And they're going in both directions, but this bee just happened to be going to the right in this video.
Yeah, I was like, oh, these bees are like flying upside down or something. But yeah.
We've got a question in the back.
Is this flight pattern just for bumblebees or other species within the Hymenoptera order? Or is it just particular to bumblebees? Because like also wasps and ants, do they have the same ability to fly like this, or is it just particular to the bees?
We only tested bumblebees. However, based on asynchronous flight as a mechanism, it's likely that any other bee or any other insect that flies asynchronously would also have the capacity to stop immediately.
How frequently do the neural activations happen? Is that when it starts up again? Is that because you think the neural activation starts it up again, the flying?
Yeah, so the immediate response is based on the delayed stretch activation, but then the recovery, I believe, is probably just new impulses to initiate the bee kind of like recovering its flight. But the immediate response, I would say, is lacking like neural activation.
Right, cool.
All right, any questions online? If you can hear me. If no more questions, we can go ahead and give Bonde one more round of applause. And then we can go ahead and have the next group start sharing their slides. This will be Cole Aikman and Ben Fargnoli from Georgia Tech and Penny.
Yeah, thanks.
All right, can everybody see and hear me? Yep.
Yes.
Yep, and slides, can see those?
Yep.
Awesome. All right, let's get into it. So the Human Robot Synergy Project was a joint collaboration between the Power Lab at Georgia Tech and the Neuromechanics Lab at Emory. So we as humans are able to adapt to changing locomotion environments. This is the reason that we can walk on flat land as well as like a rocky trail. And this adaptation also includes interactions with assistive devices such as wearable robotics. So what we wanted to look into was how people adapt to wearable robotics on the movement, metabolic, and neural control levels. So during our data collection, we were able to collect a ton of different data types all at once. This included indirect calorimetry using this metabolic mask. We had a Vicon motion capture system where we placed retroreflective markers on joints and important anatomical landmarks. We also had a split belt treadmill that recorded the ground reaction forces and also allowed the participant to be able to walk in place. We had surface EMGs on 8 of the muscles that are very important for locomotion on both legs. We had an ultrasound on the left leg that was recording the muscle fascicle lengths in the soleus and gastrocs. And then we also had a Defy exoskeleton boot that was providing the assistive torque to the ankle joint. So a lot of data at once. And our protocol for this experiment was 6 minutes of standing for the baseline, and we would have the participant walk for 6 minutes with the exoskeleton off. So that meant it was just on the foot passively, not providing any assistive torque. And then we would have the participant walk for 30 minutes during the adaptation period with the exoskeleton providing assisted torque. And then we turned it off once again, just having it passively on the leg for another 6 minutes during the deadaptation period, and then 6 minutes for another baseline. So here is a short video of our participant walking with all of the gear set up. You can imagine walking with all that stuff for 45 minutes. It'd be real fun. And then during our data collection, we had a little bit of a technical issue with the exoskeleton where the battery died and the ankle joint locked up. So our participants stumbled a little bit. They didn't fall, but they stumbled. So we decided to just turn the exo completely off and start the deadaptation period from there. That's why it's only 26 minutes instead of the full 30. And from our metabolic recordings, which records the exchange rate of gases such as oxygen, carbon dioxide, so we can see how metabolically taxing an action is. We were able to see that during early adaptation, right after we turned the exoskeleton on, it went up a little bit, so it was a little bit harder. But slowly as they adapted, it dropped down to more metabolically efficient. We would need a bigger data set to be definite, but this kind of shows that it might be more metabolically efficient to use the exoskeleton. And then for the ground reaction forces that we recorded using the split belt, we filtered it with a 20 hertz filter, and we chose that because that's the frequency of movement, especially in walking gait. And we wanted to detect heel strike and toe offs using the vertical force. So what we did is we set a force cutoff of about 7 newtons. So when the force rose above 7 newtons for about 350 points, we would indicate that as a heel strike. And then when it would drop below 7 newtons for about 350 points, that would be considered toe off. And then we had to manually check for crossovers because it's a split belt. If the right foot stepped on the left belt, it would cause this sort of like graphing error, which is not accurate data. So we had to manually go through that and take those out. And in these plots, you can see this little gap right here. It's from crossover steps. So it's not missing. We just had to take it out for it to be consistent. And in each of these graphs, we recorded 1 minute of data at a time during each of the points, just to make it simple and not so the file size wasn't a zillion gigabytes. So from the ground reaction forces, we can see that it increased initially when the exoskeleton is turned on and also when it was turned off during the lockout. And because your vertical reaction force is generally determined by the participant's weight, we can speculate that this increased just a little bit because now you're providing extra power from the exoskeleton that's allowing the participant to push harder into the floor. And then during the lockout phase where the participant stumbled, their center of mass dropped. So in order to keep themselves up, they had to push harder into the ground to accelerate themselves back up. And then the stride frequency was determined by one heel strike to the next heel strike. So we can see that when the exo was turned on, the stride frequency increased, which means they were taking smaller steps. And we kind of think that this could be because when you change the environment, the participant will naturally take smaller steps in order to be more stable, so they have more control. But as they adapt and go later into the time trial, you can see it kind of levels out and they start taking longer strides as they get more comfortable using it. And then once again, during lockout, the trip, you're shimming your feet, doing everything you can just to stay up. And then we were using some surface EMGs, and surface EMGs naturally have quite a bit of electric noise. So we needed to get rid of that with a high pass filter. And then we rectified the signal in order to make it all positive values. And then we sent it through a low pass filter that gave us this nice like encapsulating curve. And we were using the EMG to look at co-activation. And co-activation is when an antagonist and agonist muscle are activated at the same time. So in our case for walking, we were looking at the tibialis anterior and the medial gastroc. And when they're both activated at the same time, it doesn't cause any additional joint angle rotation. It kind of like stiffens that joint as well. So when we look at the EMGs for when the exoskeleton turns on and off, we can see that at the beginning, when it turns on initially, the muscles start working more or being activated more. Your brain is telling you to fire those tibs or gastrocs in order to possibly keep the ankle joint stable as it's figuring out what the most optimal way to walk is. And then similarly with lockout, as you're falling, your muscles are just firing by themselves automatically in order to keep yourself upright. And we see a similar trend with the co-activation where initially your muscles are tensing up a little bit in order to keep that stability. And then during lockout, it goes crazy while you're trying to keep yourself off the ground. And with that, I'll let Ben take over with the synergy analysis.
Thank you, Cole. So Cole told you guys a bit about co-activation. And another thing we wanted to look at in the EMG data was muscle coordination. So now instead of an antagonist muscle co-activating, we're looking at any muscles that co-activate together. And so to look at coordination, we use the muscle synergies framework to model muscle coordination. So what muscle synergies does is it uses a non-negative matrix factorization algorithm to decompose muscle activity into modules that comprise of weights and activations. And those modules are such that you can multiply these weights and activations together to reconstruct the muscle activation. And then you can compare this reconstructed muscle activation to the original muscle activity to get an idea of how well does this decomposition capture the coordination going on in the muscles. So we can go to the next slide. Cole, do you want to hit the next slide?
We need to go, are they?
Uh-oh.
All still there? Is it being?
There we go.
Oh.
I mean, headphones.
Okay.
But
what happened?
Maybe type advance the slide. Oh, there, it looks like he's trying. Oh, there you go.
Great. Thank you. And so, so when we use muscle synergies, we get these weights and these activations. And what's interesting about these weights is that they're physiologically relevant. And so the weights will show you what muscles are co-activating, and then the activations will tell you when that co-activation occurs in the gait cycle. And then also what's interesting is that when we look at that reconstruction, we can look at the variance accounted for by that reconstruction to have an understanding of how complex is the fundamental coordination pattern. And so, like I said, these weights are physiologically interpretable. And so here we can look at a 4-module solution for our baseline trial. And so we can see that each of these 4 modules corresponds with like a function in the gait cycle. So we can have a loading response module, a stance module, a pre-swing module, and a late swing module. And so when we look at these synergies across all of the trials during our adaptation experiment, we can see that there is some variation, but what we found most interesting was in the early adaptation and during the late adaptation stage, we see this de-weighting of the soleus. Now that's particularly interesting because we think that it's the soleus and the gastroc that are assisted by the ankle exoskeleton. And so we can kind of qualitatively observe these trends. And then we want to start quantifying more precisely, like how does the coordination change? And so here we look at complexity. So here we use total variance accounted for, which by 1 module. And so this will tell us how complex is the fundamental coordination pattern. And now we saw the soleus de-weighting happen during early adaptation and late adaptation. Here we see changes during mid-adaptation, late adaptation. So during mid-adaptation, we see a spike in TVAF, which is a decrease in the complexity. And during late adaptation, we see the opposite. We see a drop in TVAF, which is an increase in complexity. And so these changes are relatively small, being at 2% VAF, but it is interesting to see how much they deviate from the other parts of the trial. Yeah. So then the next thing we wanted to look at was we kind of qualitatively are able to observe some differences in the synergies from trial to trial. So can we quantify that by looking at cosine similarity of the modules during different points during our experiment? But we didn't see any trends in this cosine similarity. And so we might have expected that during adaptation phases, that those synergies are more similar compared to non-adaptation phases, but we didn't see that trend. So in summary, we found that metabolic cost and muscle activation initially increased and then gradually decreased during exoskeleton adaptation and de-adaptation. And we also found that we could use synergy analysis to further characterize muscle coordination during exoskeleton adaptation and de-adaptation. So going forward, we did our trial with one subject, and so we'd like to continue to collect for more participants. It'd also be interesting to look at if adaptation is joint specific. So now instead of just looking at an ankle exoskeleton, also adding a hip exoskeleton and seeing if people adapt differently depending on what joint is being assisted. And then also if adaptation is person specific. So how do trends in adaptation change based on personality or cognitive capacity? Another thing Cole mentioned is that we use motion capture, and we weren't able to dive into that. So we'd like to, going forward, look at the inverse dynamics from that, and also do a muscle level analysis using EMG and ultrasound, and then also use biological sensor model like the muscle spindle framework to explain adaptation. Thank you everybody for listening, and we're happy to take questions.
I have a question. Did you say that the exoskeleton that it was helping the soleus?
Yeah, the soleus and the gastroc.
I just find that interesting because I know that the soleus is more of like a postural or assist with posture. So since your subject is walking, I don't know, maybe I was just thinking that the gastroc would be assisted more from the exoskeleton. I don't know if you have any thoughts on that.
Yeah, it was definitely something we were surprised to see that the gastroc, at least in the synergy analysis, didn't change. And so it could just be this participant. It'd be something interesting to see if that is consistent across collecting other participants. But yeah, we were definitely surprised by the same thing.
Cool, thanks.
I have a few questions actually, but I'll start with, so you said when the exo shut off, was that like, it was very sudden, or was there like a progressive decrease in torque as that battery was dying? Is there data? Do you know? I mean, it seems from like, it seemed pretty sudden. There were like maybe 4 or 5 transient strides where there was a big change, but super sudden. Okay.
Yeah, it was pretty sudden, and it caused like a stumble.
So did you, in any of the analyses, explicitly separate those maybe 4 or 5 strides to see how different they were? I mean, this seems like this is unsteady movement. These are very perturbed situations. I wonder if you if you did like your synergy analysis in that, would you see something very different in the complexity? And also, if you could elaborate more on with the complexity, choosing to just look at how much variance is explained by one synergy versus maybe seeing how many synergies you need to explain like 90% instead. Like what's the trade-off in using those 2 approaches for complexity?
Yeah, so at least for those 2 approaches, it's just TVAF is a continuous measure and number of synergies is discrete. And so especially when we're looking at trial to trial, in order to pick up specifically like a 2% change in VAF, really we wanted to look at TVAF to be more sensitive. And we didn't do synergy analysis on the lockout, or at least on those individual strides, but that would be interesting. I would be curious about maybe how many of those strides are affected, and looking into that. I would probably expect a lot of co-activation during that period and maybe a lower complex gait, but maybe that's also an interesting thing to look at.
Any questions from online and Zoom? If anybody wants to speak.
I have a question about the metabolic data. Could you pull up one of the slide that shows the time course of the metabolic data? I don't know if this would be consistent across other participants, but the most striking thing to me was this the 6-minute period where they were adjusting to the exo off. And okay, so they were standing before. Do you think that, you know, during that early adaptation phase, they're still adjusting to just having the exo as well as adjusting to the propulsion provided by the exo? In other words, do they need a longer baseline period to sort of separate adjustment to the device itself from adaptation to the assistance?
Yeah, I think that's true, but at the same time, these trials are already like an hour long of walking. So I mean, there's an extent to which we can have the participant walk, but I do think that would be a good idea to have them walk longer with the basics, so they get like, because they are carrying a lot of gear, so walking with that surely would impact the metabolics. And I don't know if you were pointing towards once the X turns off, it kind of jumps again. It is like almost a second adaptation period because you're getting used to something and then turning it off is basically making another adaptation to normal walking. I don't know if that answers your question completely, but hopefully it helps.
Yeah, I think both things may be true. That early adaptation, which is what I was referring to, but that later point where people are essentially unlearning what they've learned during that adaptation period. Thanks.
Any other questions? We still have a couple minutes more for discussion, Lena.
So I'm wondering, like, we've seen some stuff with EMG where if you trick people, then like they don't adapt. So I'm wondering, actually, if you keep the metabolics up there, if there hadn't been this, I guess, kind of fortuitous lockout, do you think the metabolic rate would decrease in that exo off condition? Because it could be that they're just freaked out and they're like, I don't know what you're going to do to me next.
Well, yeah, I totally think like basically almost falling, your heart rate's probably going to spike and you're going to have to calm down a bit. But I'm not sure because this is the first like project I've done working with metabolics, but I would assume that maybe given an extra little bit of assistance from the exo, it might be a little bit more difficult to walk again, or just the mental capacity of having to relearn like how to walk normally without it could possibly make it more metabolically inefficient.
Online before we wrap up this session for today? Let's give the speaker. Great discussions, and we'll regroup online tomorrow morning at 8:40 a.m. So we're starting a little bit earlier tomorrow morning, so just keep that in mind and continue to learn about everybody's progress. I think we've already had some good seeds sown for conversations across our team. So it's been really great to see all of the progress that everybody's made. So thank you, everybody. We're going to log off on Zoom now. For now, we'll log back in tomorrow morning and we'll see you. So thank you. Bye-bye. Yeah.
She said, see you tomorrow.